Okay, welcome back. Today we're going to start with 6.3, separation of variables, and the logistic equation should be the title of your notes in your note packet. I'd like you to follow along and pause this when necessary if you want to work ahead and try a couple of the examples. So your learning objectives are going to be a little bit different, I think, than the ones I have. This is from an older document. So we're going to jump right into the first example here. So if you read over this first example, a couple things I wanted to highlight. And first thing is where it says assume that the growth rate is proportional to the population size. What that leads to, this is a really important concept of calculus, is that leads to that differential equation down here. The growth rate, dp dt, so the change in population or the change in time, is equal to or is proportional to the population size p, and this k right here is a constant of proportionality that you probably talked about in one of your earlier math classes. So the point of this problem is that we're going to work from the differential backwards to get our population model based on the fact there were 2,560 million people in 1950. It's going to be our starting point, our initial condition, and 3,040 million people in 1960. So one of the objectives here is to in this section, in this unit, is to be able to take this differential and separate the variables and develop a logistic equation from this. So let's get at it. So first thing we're going to do is we're going to rewrite this equation. So I'm going to rewrite it as dp over p is equal to k dt. I'm going to, now that I have the variables separated, I'm going to integrate both sides. The integral of dp over p, and this is p to the 1, remember, is going to be ln absolute value of p, and the antiderivative of k with respect to t, respect to time, and k is just a constant, is kt plus c. My pen is running out here, so I'm going to switch up pens here. Let me rewrite this again. kt plus c. Now, if you followed along in any of the earlier notes, I called this constant. I'm going to label that, that's a little zero below there, just to show a little bit of difference between the next constant. You'll see why I'm doing that. So it doesn't matter what you call this, capital C sub 0, capital C sub 1, capital C, little c. Really doesn't make a difference even using C. Okay, so here's what we have. ln of absolute value p is equal to kt plus c. Now, when I'm going to show you something a little bit different here, what I'm going to do is I am going to exponentiate both sides of this. So when I exponentiate both sides of this, it looks something like this: e raised to the ln of p and e raised to the kt plus c. I did something a little bit different using the definition of a log in earlier sections, but I just want to show you a different way of doing it. Same result. So now when we exponentiate the e raised to the ln of the absolute value of p, these are inverse functions, so the e and the ln are going to undo each other. We get the absolute value of p. I'm going to leave it absolute value for now. And then on this side, we get e to the kt plus c sub naught, something like that. So absolute value of p, and I'm going to, this should be pretty, hopefully, recognize this a little bit here. So e raised to the kt plus c sub 0 can be rewritten or unsimplified form like this, because when you have the same base, you add the exponents. So this would get back to this previous step if we were simplifying. Now, because this e raised to the c sub 0 is just another constant, I am going to put that in front as just my c. So this I redefine that as c, because e is a constant raised to another constant is just going to be a constant. And we have what's called our PERT equation, or you might have heard it referred to in earlier math classes, your PERT or your CERT equation. I'm going to lower the light exposure just a little bit here. Okay, so now here's a part of it I glossed over and didn't explain very well in earlier sections, is we have the absolute value of P is equal to CE to the KT. When we get rid of those absolute value, we're redefining P as plus or minus CE to the KT. Now, because we're dealing with population, the population is positive, as you can see from the stem of the question. We're only going to need, for this particular question, the positive, but it's important considering the initial condition when you are deciding to remove the positive or the negative in front there. So here's what we have for our population model. Now we know that in 1950 there were 2,560 million. So what that means is there were 2,560 million people when time was 0. I'm going to call 1950 year 0. So 1950 is year 0. Okay, so what that means is, let's see what we have. We were 2560 equals C, because e to the 0 is just going to be 1. So we're going to go back up here. We have P is equal to 2,560 million, we're in millions here, e to the KT. The next thing we know is that there were 3,000, and by the way, I'm getting this information, I think you can recall, but I'm getting this information from up in the stem of the question. So there was 3,040 million people. Initial is 2560, e to the k, and the time that it took to grow from 2560 to 3040 was 10 years, from 1950 to 1960. We solve for k. We divide both sides by 2560, e to the 10k. We solve, we're going to rewrite this as a natural log. So a natural log of 3040 equals 10k. We divide both sides by 10. So we get this number, which if you have a calculator, feel free to find a decimal approximation. I am going to leave it just for the sake of time like that. And then I rewrite my model. I have my model and I have my, remember they asked us in the original, hopefully you read over the question prior, was what is the relative growth rate K? So here is our relative growth rate. That is our growth rate relative to the 1950-1960 data they gave us. So there's our growth rate. So P is equal to initial population 1950 is 2560. E raised to that ln of 3040 over 2560 over 10. That's my K. And my time is my independent variable, with population being the dependent variable. And this is our model, and that pretty much answers our questions. There's a couple of things they asked you to predict the population in 1993. Well, 1993 would be what? 43 years after 1950, so we'd have to plug in T equals 43. So population of 43 is equal to, I got 5,359.997 million. I just plugged in 43 for T, and then 2020 means, let's see, how many after, that's 70. It's equal to T. So P of 70 is equal to 8,524.625. And you can check my math on that and make sure I got that in the screen. Sorry about that. I also have a key available on Classroom where you can, if you need to take a look at this, or pause the video. Okay, so our goal then for today is just to do one more example. So if you turn the page over, and the final example that we're going to finish up with, this part 1 of this 6.3 video, is find the general solution of x squared plus 4 dy dx is equal to xy. So this is a differential equation. we have to separate variables because that's one of our objectives here. So we're going to start off rewriting it dy dx is equal to xy over x squared plus 4. I'm going to move the y over to the other side, dy over y, and the dx over to the side, x squared plus 4 dx. And we have accomplished that goal, separating variables. We're going to find the antiderivative of both sides. We should be pretty comfortable with rewriting the antiderivative dy over y as ln of the absolute value of y. And then this is going to be a u substitution question in this one. U is equal to x squared plus 4. Du is 2x dx. And I have an x dx up here, right there. So this is going to be 1/2 du is equal to x dx. And again, I'm hoping that you're comfortable with here. And when we substitute it back in, we get 1/2. We get a du. And we get a u. So ln of y, ln of absolute value of y is equal to 1/2 ln absolute value of u plus c. Ln of absolute value of y is equal to 1/2 ln of the absolute value of x squared plus 4. Now we can get rid of those absolute values because x squared plus 4 is going to be positive at all times. So looks something like this, ln of, and now the other thing is we can put the 1/2 up in there according to the property, the exponent property of logarithms. So 1/2 plus c. I am going to again show you the technique of exponentiating both sides. So e, so e raised to the ln of absolute value of y just becomes absolute value of y. And then this guy becomes e to the ln of x squared plus 4 to the 1/2 times e to the c. Call this c sub 0, c sub 0, c sub 0, c sub 0 there. And then redefine this constant as c. And we get, let's go over here, we get the absolute value of y is equal to c. And then if you remember, let's go back here, e to the ln, those are going to undo each other. So essentially, I hate to use that word cancel out, but that's what's going to happen. We get x squared plus 1 raised to the 1/2. So now y is equal to plus or minus c x squared plus 1 to the 1/2. And again, the plus or minus when we're solving for absolute value is something I glossed over in earlier sections. I apologize for that and trying to remedy that now. And that is our general solution because it has a c in it. And notice we do not have an initial condition like we did in the last problem to work with. So we stop there with the general. Y is equal to plus or minus c times x squared plus 4. I have a plus 1 because my writing is not very good. So x squared plus 4 raised to the 1/2. I'm going to stop there for today, about 13 minutes, and then we'll come back for the second part of the notes and finish with the examples here.